Welcome back, Math 152. Last time we looked at sampling distributions of the sample mean. This time we're going to take a look at proportions and see if we can come up something like the central limit theorem for proportions. So suppose we have a population and we know something about a proportion. Remember, proportions are more along the lines of categorical data or qualitative data. The percentage of people who like blue, the percentage of people who like yellow, what's your favorite car, those type with a certain percentage of people in a survey type, sampling survey type. So we've got something, some proportion, and I'd like to say something about samples. If I draw a sample about that, what does the proportion look like from that, and can we calculate probabilities based on those? So in a population, the proportion to have a certain characteristic is called the population proportion. So the population proportion is denoted by P. Sometimes this is also pi. If you know what the pi looks like, the Greek letter pi, it's also used as pi as the symbol. In a simple random sample of n individuals, let X be the number in the sample who has the characteristics. The number that like yellow, the number who like blue, the number who prefer Ford. So that's the number out of the sample size, and what we call that is the sample proportion. The sample proportion, I'm going to use the little symbol P hat. Okay, so this is the sample proportion. Population proportion is the big P. So here's an example. A computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everyone in the city, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops, so the sample proportion is 35 out of the 100, 4.35, 35% of the people. The proportion of people in the entire city who owns laptop is the population proportion P, and we don't have that value. So I'd like to see if there is some relationships to P, the P hat, and sampling proportions. So here's the overall population, and if we knew, let's make this statement, if we knew what the population proportion was, we necessarily wouldn't have to go grab a sample to find the population. But I want to find the relationship between a population proportion P and different samples. So if I went and grabbed different samples, each one of these P hats would probably be a different proportion by, a small percentage. The population proportion is fixed. If we knew all the data and all the percentage of the people who like that, we know the P. So the P hats, though, are going to be different. So I may want to call this P hat 1, P hat 2, P hat 3. Okay. So just like we did before with the sample mean X bar 1, X bar 2. If several different samples are drawn from a population, they are likely to have different values of P hat because the value of P hat varies each time a sample is drawn. You may get more, you may get less. P hat then we can consider as a random variable, and it has a probability distribution just like we did with the X mean. The probability distribution of P hat is called the sampling distribution of the sample proportions. So consider tossing a fair coin 5 times. This produces a sample of size n equal to 5, and all we're talking about is they have to be fixed sample sizes. Different samples, but it's the same sample size. Each item in the sample is either head or tail. The proportion of times the coin lands on heads is the sample proportion P hat. The probability that it lands heads each time is 0.5. Therefore, the population proportion of heads is P equal to 0.5. Next, we look at all 32 possible samples that can be constructed. So remember, we know what from classical probability, the population proportion would be 0.5, 50% heads, 50% tails. But if we flip them 5 times, here's all the different variations that we could come up with. and this would be the proportion of the heads. Okay, and we calculated all of these out. This basically develops a population proportion and the sample size from here. Okay. So the previous table, the mean of the sampling distribution is mu of the p-hats. The mean of the p-hats, the mean of the sampling, the sample proportions was 0.5. If we just averaged all of those out, some of them were 0.1, some of them are all the way through, and we just basically did the mean of these. And it turns out the mean of the population, the mean of the sampling proportion, is the very same as the population proportion. In this case, it was the classical probability proportion of 0.5. So here, just like we use symbols for the mean of the sample means, we're going to use this as the mean of the sample proportions. Okay, the mean of the sampling distribution of p-hat is denoted by mu of p-hat and equals the population proportion. So here we're going to be able to do something making statements about a particular p-hat. If we went and grabbed a particular sample, how would that compare? And this would be the mean that we would use. And the standard deviation that we're going to use is related to the p as well, the population proportion. And it turns out that the standard error, or the standard deviation of the sampling distribution of the sample percentages is proportions is the square root of p 1 minus p over n. So this is like if this was 0.4, 1 minus 4 would be the 0.6, 0.5, 0.5, 0.7, 0.3, all over the size of the n. And that would be our standard error of the sampling proportions. So let's consider a problem. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see where they win a prize. The proportion of tickets that are winners is p is equal to 0.25. A total of n equal to 70 people purchase soft drinks between noon and 1 p.m. on a certain day. Let p hat be the proportion that win a prize. Find the mean and standard deviation of the sampling distribution of proportions. So the population proportion, p is equal to 0.25, sample size, n equal to 70. The mean of the p-hats is just p, which is 0.25. And the standard deviation of the p-hats, p1 minus p, the 0.25 is from the 25% of the population proportion, 1 minus 0.25 over 70, and that gives us a standard error again, or standard deviation of 0.0518. So it turns out, here's the probability histogram for the sampling distribution of p-hat for the proportion of heads in 5 tosses. Okay, so this is basically, we went back and we did our tosses of coins for 5. And if we basically went through and basically did 50 tosses, number of tosses, the sampling distribution of p-hat is more closely approximated by a normal curve. So here's the 5 tosses. If we built that, here's if we did 50 tosses. This is, and it would start looking like a normal curve. So basically, what we're saying is that if we have a big enough sample size, that we can do population proportions based on this as well. It's not really the size that we're going to look through here. It's going to be a variation of that. So when p is equal to 0.5, the sampling distribution of p-hat is somewhat close to normal, even for a small sample size like n is equal to 5. When p is close to 0 or close to 1, a larger sample size is needed before the distribution of p-hat is close to normal. A common rule of thumb is that the distribution may be approximated with a normal curve whenever n times p and n times 1 minus p are both at least 10. So before, all we had to do was look at the n. If it was bigger than 30, we were good. here we're going to have to look at the proportion and make sure if I multiply n times p and n times 1 minus p, both sides of those are at least 10. That the size of this thing is at 10. So here's the central limit theorem for proportions. We saw it for the means, and now here it is for the proportions. Let p hat be the sample proportion for a sample of size n from a population with a population proportion p. If n times p is greater than or equal to 10, n times 1 minus p greater than or equal to 10, then the distribution of p hats is approximately normal. This is the distribution of the sample proportions is approximately normal. The mean of that distribution, the mean of the p hats is just p, the same thing as the population proportion. And the standard deviation of the sample proportions, sigma p hat, is the square root of p times 1 minus p all over n. So a sample of size 20 is drawn from a population with population proportion p is equal to 0.7. Is it appropriate to use the normal distribution to find the probabilities for p hat? So I would want to multiply 20 times the 0.7, and then I'm going to multiply 20 times 0.3 and verify that they're both bigger than or equal to 10. So n times p, 20 times 0.7 is 14. I'm good there. But if I do this one, 20 times 0.3, I'll only end up with 6. And I needed both of those numbers to be bigger than or equal to 10. So I can't use the central limit theorem to answer probability questions about sample proportions. Here's a 55. If I do with this, can I do this? With the population proportion as p is equal to 0.8, is it appropriate to use the normal distribution to find probabilities for p hat? 55 times 0.8 and 55 times 0.2 are the numbers that I'm going to look for. So n times p, the 55 times 0.8 is 44. I'm good, bigger than 10. N times 1 minus p is the 55 times 0.2, only equal to 11, but they're at least 10, at the least, the very least is 10. The distribution of the sampling proportion is approximately normal, and I can use the central limit theorem. So let's go through and calculate, see what the problems look like using sample proportions and computing based on the central limit theorem. So according to a recent Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans is taken, what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30? So I go out and I grab one particular random sample of 100, and I'm asking it based on the sampling distribution, would it be greater than 0.30? What would be the probability that that particular sample would be greater than 0.30? So we need to check our assumptions. N times p, 0.27 times 100, and then 0.73 times 100, the 1 minus 0.27, the 0.73. That would be greater than 10 on both ends, so we could use that. And now we just need to know what we're going to use. Normal CDF. I need the mean and the standard error, or standard deviation. So the mean that I'm going to use is the mean of the sample proportions. That's just equal to the population proportion, 0.27 from the statement. And then our standard error of the sampling proportions is p, 1 minus p over n. 0.27 was our population proportion, 1 minus 0.27 over 100. That's just going to be 0.044396. And from our calculator, our technology, this is just saying, here's our left endpoint. I want to know, is it greater than 0.30, greater than 30%? So I want this to be the min, and then all the way out to 1e to the 99, 10 to the 99 is basically all the way out here in this tail. Okay, our mean, 0.27, that's the population proportion. And here's their standard error or standard deviation of the sampling proportions, the 0.044396. And that tells us that area, same thing as the probability, the same thing as the proportion in here of 0.2496. In the 2012 U.S. presidential election, 51% of voters voted for Barack Obama. If a sample of 75 voters were polled, would it be unusual if less than 40% of them had voted for Barack Obama? So let's check our assumptions. N times P, N times 1 minus P. Both of these are bigger than or equal to 10. So now I just need to know the mean of the sampling proportions. Well, that's basically the population proportion, the 0.51. The standard error or the standard deviations of the sample proportions, P 1 minus P over N square root. This is 0.51, 1 minus 0.51 over the 75, the sample size that we're pulling from. That would be 0.057723, and I'm saying less than the 0.4. So here is from negative 10 to the 99th, all the way out here in the tail, up to the 0.4. I'm asking is that, what about, would it be unusual for 40% or less, 0.4? Here's the mean of the sampling proportion, the standard error of the sampling proportion that we just calculated. So that error would be 0.02, or the probability of 0.0283, less than 0.05, so that would be very unusual. So the probability of the sample proportion of those who voted for Barack Obama is less than 0.40, is 0.0283. It would be unusual for the sample proportion to be less than 0.40. So here's some important formulas that I've added to this slide. This is basically from the N matter. Before we were doing based on just the general z-scores, x minus mu over sigma, and how to convert from a z-score to a raw score, z-score from a raw score. Here's the standard deviation of the sample mean. Remember, that was the standard error or standard deviation of the sampling mean with sigma over the square root of n. Here was the z-score based on that. I took my x bar, what I was concerned about, minus the mu, that was the mean of the sample means, turned out to be, divided by the standard error of the sampling means. And then we did the sample proportions, and I just wanted to put these back in here. That here was the mean of the proportions was just equal to the population proportion. Here was the standard error of the sampling proportions, sample proportions. And if I want to do a z-score, I'm just going to do p hat. The one that I'm concerned about is that what would be the probability of it being 0.3 or less, 0.7 or more, between 0.4 and 0.7. That's the p hat minus the mean of this. This is the population proportion over the standard error of the sample proportion. Okay. So I hope that helped. See you next time. Have a good day.